just to sort of summarize our condensation reactions, let's talk about what the reactants are and what type of product can be formed in each of these reactions. So if I have an aldol reaction, I need to have some sort of enolate plus an aldehyde or a ketone. So if my enolate looks like R, C double bond O, and then a C minus next to that, that's going to add to some sort of aldehyde or ketone, like that. And our product can be a beta hydroxy aldehyde or ketone, where our disconnection comes right there. Okay? Or if we dehydrate it, we can make an alpha beta unsaturated carbonyl compound, right? An enone. So these are the products you look for. If you have beta hydroxy aldehyde or something like that, or an enone, imagine retrosynthetic disconnection happening between the alpha and the beta carbons. And that can come from an enolate and a carbonyl. For the Claisen reaction, we can imagine having two esters be the reactants. So RC double bond O, OET, for instance, CH3, C double bond O, OET. To do that, remember the enolate will add, and then that will kick off the ester leaving group of the electrophile, and that will regenerate a carbonyl. So what we end up with is a beta keto ester. Just like that, right? That's called beta keto because here's alpha, here's beta. The retrosynthetic disconnection there happened again between the alpha and beta carbons of the remaining ester. We can do a Claisen-like reaction if I have just a regular enolate plus an ester. Okay? Say that I have similar sort of ester here that can accept, right? That's the electrophile. But now I just have plain old carbon enolate. Okay? We end up with a very similar product, except instead of having an ester in the final product, it's just a beta diketone. Right, with the other R group coming from the enolate originally. For the Michael reaction, we can, for instance, have a beta keto ester plus an enone. Right, if I have beta keto ester, right, R C double bond O, CH2, CO2ET, right, that can form the enolate that's stabilized, and then I can react that with some matter of enone, like that. Our product is a 1,5-diketone plus the extra ester group. So C double bond O, that's 1, 2, 3, 4, 5. But then we still have that ester group attached, alpha, to the original enolate. Right? So 1, 2, 3, 4, 5. However, if we have hydronium and heat, we can decarboxylate to make a regular 1,5-diketone. All right. A similar reaction is if instead of having a beta keto ester, I just have a regular beta diketone. Like that, plus the enone, we have no opportunity for decarboxylating anymore. We end up with a triketone. 1, 2, 3, 4, 5, right? It's still 1, 5. But then I have, where this temporary ester group is, I have an extra ketone right there. I say 1, 3, 1, 5, 1, 5 because we have two carbonyls that are 1, 3 to each other, right? That came from the original beta diketone. And then both of those are 1, 5 to the one that came from the enone. Now, the Stork reaction with an enamine plus an enone will give us just a plain old 1,5 diketone. So Nr2 plus the enone after we get rid of after the enamine reacts like a nucleophile, then we hydrolyze it, we get a carbonyl in its place. 1, 2, 3, 4, 5. Okay. So hopefully you can use this to sort of synthesize together a lot of the things that happened in this chapter. Oh, I forgot to draw the retrosynthetic disconnections for the Michael reaction. That's again between the carbon 2 and 3, between alpha and beta, right? In each case, every single one of these has a disconnection between alpha and beta of the original enolate, right? So alpha, beta, alpha, beta, just like that, okay? So here's a little practice for you. I'm going to draw some reactants, and as practice for you, you can draw the product. So I have each of these reactions we talked about, and I'll give you an example of an intermolecular, right, which just means we have two molecules reacting, versus an intramolecular, where I have only one molecule reacting, and it closes in on itself and makes a ring. So here's an intermolecular aldol reaction that'll work just fine. If I have benzaldehyde, so pH C double bond OH plus acetone. Okay. Those two can react together to make a aldol product that'll work just fine. For intramolecular, I can have an aldehyde and a ketone as part of the same molecule. So let's start with an aldehyde on one side, and then 1, 2, 3, 4, 5, 6. I'm going to make 6 carbons. 1, 2, 3, 4, 5, 6. Okay. And 1, 2, 3, 4, 5. The carbonyls are 1, 5 to each other. You should be able to identify where an alpha carbon is 5 or 6 away from a carbonyl. So for the Claisen reaction, let's do a standard Claisen with two esters. Here's methyl formate, C double bond O, OCH3, plus methyl acetate, CH3, C double bond O, OCH3. Okay. And it's a mixed Claisen reaction, but there's only one type of alpha hydrogen there, so it'll work just fine. For an intramolecular Claisen reaction, that's called a Dieckmann reaction, that has to have a diester. So CH3O, C double bond O, and then 1, 2, 3, 4, 5, 6. So 6 carbon. 1, 2, 3, 4, 5, 6. So dimethyl hexane dioate will undergo a intramolecular Claisen reaction. So a Claisen-like reaction where we have just a regular enolate reacting with an ester could be something like cyclohexanone reacting with ethyl benzoate. An intramolecular Claisen reaction could be a methyl ketone on one end, and then 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. like that. Let's do a Michael reaction with an ester. So here is ethyl acetoacetate. React that with our enone. Okay, 1, 2, 3, 2-propenal. That'll give a nice Michael reaction. This gets a little trickier, but I can do an intramolecular Michael reaction. Let's start with an aldehyde on the end, and then this is a 1, 2, 3, 4, 5, 6, 7, 8 carbon compound. 2, 3, 4, 5, 6, 7, 8. Okay. The aldehyde is actually an enal. Okay. So like an alpha beta unsaturated aldehyde. And then on carbons 6 and 8 are carbonyls, the last one being an ester. Okay. So that one will be kind of fun to make a ring out of. So for these Michael reactions, draw both the products with the ester in them and then decarboxylate. So show the products with and without the temporary ester groups. Here's some Michael reactions where we have just diketones reacting, no ester groups available. Right, here's cyclopentane dione. Let's just react that with our little aldehyde enone. Here's an intramolecular Michael. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 carbons long. 4, 5, 6, 7, 8, 9, 10. Right. Carbon 2 and 4 are a diketone. Let's put geminal dimethyls on 6, and then let's make an enal out of the other side. That'll be fun. Finally, let's do some Stork reactions here. This is 1, 2, 3 methyl 2-butanone. So you're going to have to make the you're going to have to figure out which direction the enamine will form on there, but it's just a regular single ketone. And then, just for fun, let's have that adding to a enone analog. Okay. This is I don't know what we call that, vinyl nitrile, right? CC double bond with a nitrile CN attached. Okay. We can do an intramolecular Stork reaction. Let's do 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. Methyl ketone on one end, and then nitro group attached to a double bond on the other end. Should be able to successfully do a Stork reaction. Yep, with that. Okay, so have fun with that. Give each of those a try on your own. See if you can get products out of each of those. I will have full products drawn in the notes that you can print out on this to check your work. So that's it for this chapter.